All right, you can take over, Aaqil.
Yeah, first of all, I'm Aaqil, and the topic I'll be taking today is prototype networks. Before we go dive into prototype networks, first we need to understand a few terminology. So, first of all, let's start with few shot learning. So, what is few shot learning? Basically, it's a kind of concept in which we aim to train models such that they can generalize to new tasks with only few labeled samples. And this is very important because in quite a few real life scenarios, we don't have much data to work with, at least for a few specific classes. So, in those cases, few shot learning is very much required to achieve some level of accuracy. And yeah, so as I mentioned earlier, the challenges that we currently face, or what few shot learning aims to solve, is scarcity of labeled data and models not being able to generalize quickly. And a few examples is recognizing a new object after seeing only 1 to 5 examples. So, for example, a model does not know, let's say, what a ball looks like, but after seeing only 1 to 5 pictures of what a ball looks like, or training only 1 to 5 samples, if you now give it a collection of images to test on, it should be able to easily recognize all the balls from that collection of data. So that's one example. And then personalizing a voice assistant with minimal data. Um, so like a new user starts using a voice assistant, it should achieve maximum personalization in a minimal amount of time. So those are a few examples of where few shot learning takes place. And how we aim to implement few shot learning is through a concept called meta learning. Let's go with the definition. Meta learning literally means learning to learn. And here we train models to learn efficiently from limited data. So we use the few shot learning idea over here and we actually make it work using meta learning. And how it works, models are trained over a distribution of tasks, not a single task. So while we might be given a single data set, we can convert it to multiple tasks, because let's just say we have a data set with multiple classes, for example. We can train it, we can like sample the classes. For example, if there are 10 classes in a data set, we can take 3 classes at a time and train it in episodes of 3 classes per episode. And so we don't need to limit ourselves to just one single training session having all of the classes and so on. And the goal of meta learning is what future learning aims to do: generalize to unseen tasks by leveraging task distribution knowledge. So, by training over a distribution of tasks, it actually learns what the data distribution of the entire data set. And I'll be showing an example soon after going through this PPT. So, an analogy to help you understand is how humans can learn a new skill by relying on prior experience with related skills. So, Python was the first language a couple of us might have learned, right? And then in college, we would have been introduced with Java. Now, Java isn't exactly similar to Python, but it does incorporate a few core concepts. And even so, relying on this kind of similarity, we actually are able to learn Java quite fast than a person who has no introduction to computer programming. So something like that. Now, few shot learning and meta learning. So how we use meta learning to implement few shot learning stuff. So how to few shot learn a data set or something. So we essentially sample the training set into multiple tasks, and I'll show soon through the code how that is done. And then we take a support set and query set. So support set is where we train the task, and query set is the set, a disjoint set where we evaluate our model that is being trained, and we backpropagate the loss from the query set. That is how it goes. And yeah, the objective over here, quickly adapt using minimal data from the support set. Now we go to prototypical networks, and missed a slide over here. I didn't add it yet. So meta learning has a few main techniques. The first technique is MAML, model agnostic meta learning, and the second class of techniques is called metric based methods. So MAML is a separate topic which somebody else could take in the future, or I might take it in the future. Metric based methods use a single metric to help classify the data. So what prototype networks use is the mean embeddings for the class, as you can see over here, and why it works. So we assume that the data points for each class are revolving around a single prototype, a single mean, you could say. So let's just say cats and dogs, for example. All cats have something in similar. That is the assumption. And in reality, that is actually the case. And that similarity is essentially, you could say, the class mean or something like that. And the same goes for dogs and so on. You could think up of many examples for this. And classification is based on proximity to these prototypes. So we compute a mean prototype. If we want to classify or perform inference, we only need to find the similarity to all of the prototypes that we have computed. And the key advantage over here is it is very simple yet effective for few-shot learning. Now, if you recall, I did mention something called MAML, model agnostic meta learning. Now that is actually pretty good, very good method, but it is computationally expensive. Whereas prototypical networks, on the other hand, are not that expensive computationally for training and inference. So that is one main advantage of prototypical networks. Now, how do they work? So it essentially learns a feature extractor to map inputs to an embedding space. And in the example I'm about to show you, I use the MNIST dataset. So I'm basically mapping the input MNIST images to some kind of embedding image. So it's basically an encoding function, you could say, except that the encoder actually trains using prototypical methods. We'll look into that soon. Prototypes compute the mean of embeddings for each class in the support set. Support set I'll show you in a bit. So hold on until then. Distance-based classification. So as I mentioned earlier, we compute the distance from to each prototype, and whichever has the least distance or maximum similarity, we will classify the classes to those prototypes. And loss functions. We use cross-entropy loss normally. You could change your loss function if you're using PyTorch or any PyTorch and experiment with different things. But for now, I'm using cross-entropy loss, and I think it is also what is mostly used for most prototype networks. And prototype networks in action. So I'll just quickly go. Yeah. So this is the notebook that I'm using, and standard PyTorch functions. I do suggest you guys to learn PyTorch if you haven't already. It's especially useful if you want to really have customization in your model training and all, because TensorFlow is good for the standard training and standard methods. But if you want to research new methods, for example, you're all part of the research group, right? DSC research. Torch will be extremely helpful in adding that customization. Now here in this cell, we're just loading MNIST through the URL transforms, and it basically created this data folder, data MNIST raw, and so we have our data set, train classes and test classes. So the training classes that I've taken over here are classes 0 to 7. As you know, MNIST is a data set having images of numbers from 0 to 9. So I'm taking the images of numbers 0 to 7 for training, and I will be testing it on the numbers 8 and 9. You might think, I'm not even training on 8 and 9. How can I test it on 8 and 9? So that is essentially what prototype networks actually aim to do, what few-shot learning methods aim to do. I'll just show you in a bit. And I created a simple function for sampling support and query sets. Now this sampling occurs every episode in training. You could say every epoch. So every single epoch we create a sample. So here we have two key terms, N-way and K-shot. So these are few-shot learning terminologies. By N-way, we mean that the model learns N different classes. And by K-shot, we mean that the model learns K examples per class for each of the N class. So each episode has N times K data points. That is essentially what this function takes as input. Query per class. So I also mentioned the query set, right? This N times K is for the support set, what the model uses for training. And the query per class is basically the K value, but for the query set. So these many query samples per each of the N classes. Now we use random to randomly select classes from the training set. In this case, for training, we just take the train classes. The data will be train classes. And yeah, we select n number of random classes and replace equals to false, of course. And initialize empty lists. And you can view the function later. I'll send the Jupyter notebook in the group later. Define prototypical network. It's a very simple convolutional network, just three convolutional layers, and 32, 64, 64, and extremely simple. And that is essentially one of the advantages of prototype network, right? It's very simple. And we don't have a classification head over here because we are using a metric based method. We are computing distance. So this network essentially tries to map our input image to a distribution of embeddings. And those embeddings are basically learned in such a way that classes, embeddings having the same class are grouped closer together, and those of different classes are not grouped close together. Then model initialization. Here I have used n is equal to 3, k is equal to 1, and yeah. So support embeddings. We pass the support images through the model, and if you see the output of the model, it's basically an embedding. And query embeddings are again passed through the model. So now we have our embeddings for support and query. And we take the basically this code is to handle one specific problem I encountered. So if you sample random classes, if you have worked with softmax before, if you want to work with 9 classes, then it expects labels from 0 to 8. But since I'm randomly taking the class labels, so even if I take like 5 random class labels, if one of them is from class 7, for example, then it gives me an error. So I had to use a bit of code over here. For class and unique classes, class and CLS embeddings is equal to support embeddings. So this is basically a Boolean filter over here. You can explore this part. Query labels, same thing. And now compute distance. So here I've used a function called cdist, which is there in Torch. We are finding the distance between query embeddings and prototypes. So where does this prototype appear? Over here. So we initially have an empty list, and for each of the classes, we take the mean. CLS embeddings dot mean dim equals 0. And so the mean of all these embeddings is the class prototype for this particular epoch or training episode. And we compute the distance with the query labels and backpropagate the loss and so on. So the loss is essentially cross entropy of the distance. We take minus distance over here. If you know how softmax works, then or how cross entropy works, then negative distance needs to be used. You'll understand. I'm saving the loss to a list over here, so I can later display the graph. And yeah, 3-way one-shot learning. So the loss is initially more than 1, and it comes down to around 0.3, 0.3, 0.4. Now I have my evaluate function, so I'm going to evaluate on the test data. And if you recall, the test data are the numbers 8 and 9. So set the model to evaluation mode. This is a PyTorch thingy, and save the accuracies over here. Torch.nograd is another PyTorch thing for episode in range number, number of episodes. So here for inference, what we do the same thing. We pass support and query, and here we don't learn from the different tasks. Here we take only one specific task, and since it is 8 and 9, our n value is going to be 2, and our k short is going to be similar to what we used for training, and in this case it's 1. So we are going to few shot learn during inference for each of the classes. So for 8, we're going to take only one shot, that is one example to learn. And for 9, we're going to take one example to learn how to classify 8 and 9. And then we infer the rest of the data points. So unique classes, then embeddings, and then we save the prototypes over here. and yeah, compute distances and predict. So arg min over here. So we're basically taking the minimum distance and mapping that to the, and then accuracy is equal to Boolean function and then few functions applied over here. Now outside the training loop, we take the mean of the accuracies list over here and display. So now if I run this function, 81.33% accuracy. Now, one question which you might have is what is the best n value and what is the best k value? So, if you want to generalize your model very well, then usually it is recommended to have a higher n value. So for our training data set, we have 8 classes. Let us just put the n value to 5. So it takes 5 classes at a time per episode. And for the k-short value, it depends on the kind of data you are having for testing, or what you want to predict on. If you don't have much data, then you have to use a lower k-short value. But most cases, you will have a bit of data to work with, quite a bit of data. So let's just put this to 4, for example, and try it out. So as you can see, it's much more stable, the loss. And by the end of 100 episodes, the average is around 0.1, 0.15. And before the accuracy was 81.33. Now let's execute the evaluation and see what the test accuracy is. It's 93.10. So this is how you can change the n value and k value to achieve higher accuracies. K value depends on the task that you are given, how much data you have for testing per class, and the n value, the higher it is, the better. The n value for inference has to be the number of classes you're going to few shot learn, but the n value for training is generally recommended to be higher than the n value for inference, because this allows a model to generalize better. And yeah, that is the demo. Few more slides to go. So yeah, this is actually what's happening. So originally, these classes might not have been distributed in such a way, but after going through few shot training, it essentially learns to compute embeddings for each class in such a way that as long as an embedding is there for the V1 class, for example, they will be clustered around the mean for the V1 class, and so on for any other classes that are learned during the training. And advantages: simplicity. You don't need memory or any complex optimizers, meta optimizers. You will learn about those if you explore MAML. Those are not used for prototype though. Its prototype is actually very simple and only requires computing means and distances, and that's why it's efficient. Few shot generalization performs well with minimal data. You probably have seen. I have used only a very low shot value. Limitations. So now the main limitation over here is we are assuming that the clustered data, our data is clustered, or it can be easily mapped to a clustered distribution. So that is one assumption. And this, if this assumption fails, then our prototype network will not perform that well. And fixed metrics. So we only use a fixed distance metric over here. So if like our assumption fails and our distance is not very good for the data set, then prototype networks will not work well in that case. Now, most of the times, our assumption, this assumption that all data points are from the same class, is actually valid, because I used the example of cats and dogs earlier. Cats do have, in fact, many similarities with each other and are different from dogs. Therefore, it is safe to assume that for most real life tasks, even if the dataset is not initially able to be clustered, our model can learn embeddings in such a way that they naturally form clusters. But anyhow, these are the limitations of prototype networks and applications. As mentioned at the beginning, future learning is applicable in scenarios where we have limited data to work with. So personalization in AI assistance, medical imaging, species classification, low resource NLP tasks. These are all tasks which we don't have much resources, much data to work with. As for this medical imaging, I believe some of you are part of the computer vision group that DSC research is, one of two DSC research groups. So yeah, we can experiment with prototype networks for that particular task. Future directions combining with attention, self-supervised learning, etc. You can explore those. There are many research papers that have implemented other changes to prototypical networks. And yeah, that's all for this presentation.